Okay, so yeah, so today is the last part, and which is QVC or QNN. So all that we have learned till now, from data encoding to what is classical machine learning to what is quantum kernels, how to use that. And after having learned all things, this is the end thing. And in this thing, there is nothing much theoretical. It's mostly how you apply all those things and just put up a circuit so that you could get the result out of your data. So it's a very short lecture, but this is what it is. Okay, so first, because before that we need to know what is QVC and what is QNN. So first thing is, what is QVC and what is QNN. So what is just one second. Yeah, okay. So what is QVC? So QVC is any quantum circuit by which you want to get a value on an observable. It's as simple as that. A quantum circuit by which you want to get a value, a simply one value on an observable. So suppose O is your observable. Is my pointer visible here? Can you see my mouse? Okay. So
Yes.
if O is my observable, you have any function that you define by psi theta. You get a part of that observable on O. Simply, that is your QVC. Now you can apply a cost function to it. So here C theta is your cost function. When you apply a cost function, you just train your data in such a way that you keep on getting some good values. Okay, I'll show you a code working also. Just hold for some time. So I'll show you two codes today. One for a real application on an image representation, another one on how this could be used in another set of classification problem. So this is your QVC. So any circuit with an observable is your QVC. Finished. Now, so why is it called variational? Because in QVC you can have parameters which you can vary. So see, we know there are two kinds of parameters. One set of parameters that we cannot change, another set of parameters that we want to change. So a circuit which has parameters that could be varied, that could be approximated according to the system state, is a variational parameter circuit, and VQC uses that kind of variational things, hence it is VQC. Okay, so in VQC, the simple steps will be to load our data, to create a trainable function having some weights and measures, and then to get a measurable output out of that. That is simply VQC. Okay, now a QVC. Now, what are the different types of QVC? So we have VQE, QAOA, VQC, QNN, and there are many other subparts of it. So we won't go in that depth, but we will restrict ourselves to these four portions. We are mainly interested in QNN. So I'll just give a quick intro to this thing. So VQ is for finding out the energy state or energy Hamiltonian. So it is popularly known as variational quantum eigensolver. So see, the H here represents the Hamiltonian of a system. Hamiltonian is an operator that is used to calculate the energy. So VQE is a kind of QVC that we use for finding energy. Now, QAOA is another set of VQC algorithm, QVC algorithm, which is used to find roots or used to find the best combinations possible. Suppose you have 3-4 points and you want to cover all of those. So how will you create a network between them so that you can finish it in a faster and more efficient way is determined by algorithms like QAOA. Next, you have variational quantum classifier. So that is VQC. So VQCs are also used. It's similar to neural network. It's similar to quantum NN, but the only problem here is it uses only trainable variational layers, and it does not resemble exactly a neural network kind of architecture. So VQC and QNN are almost similar with a simple minor difference between them. And at last we have our QNN. So QNN represents a neural network, exactly a neural network. And how a neural network would behave is similarly how a QNN would behave. But other things will be same. So you have a embedding, you have another function, you have a observable, and you have a cost function, a classical cost function by which you optimize your circuit. And as I told you today, mostly our work will be on the basis of code demonstration. So we need to go for the 4 parts of it. So for the 4 parts of Qiskit pattern, first one is mapping the problem to a quantum circuit, optimizing for the quantum execution, executing on Qiskit primitives, and post-processing to return the classical data format. Okay, so now we will go for the code understanding. Just bear with me. Just bear with me. Can I stop the share? Can I pause the sharing? Is my sharing paused?
We currently see your desktop and your pointer is not moving, so probably paused.
We see your desktop and your pointer is not moving.
Okay, okay, okay. Great. Just 1 second. It's almost done. Let me load the codes. Just 1 second. Okay. Okay, just 1 second. Another part has to be loaded. Okay, yeah, almost there. Okay, now can you see my screen? Is my screen visible now? Okay, so let's look at it in this way. So we have a quantum image. Now, why we are saying a quantum image? So suppose we created a checkerboard kind of image, and suppose we created a circuit. When we are saying quantum image, that means we are encoding each value pixels of the image to the encoding part of the circuit. So this part at the front, this is my encoding part. Is that clear? Now, suppose I'm initializing the parameters as 0. So keep one thing in mind, that these are my hyperparameters. Hyperparameters mean those that we won't be changing, those which are fixed. So image values are there. Hyperparameter means the image values converted to the angle values. So we are using angle encoding here. Converted to the angle values won't change. So they are hyperparameters. Next, we have parameters. That means we want these values to change, and we have initialized them. That is, every weight that you want to put has to be given some initial values, and for all the angle values we have put here 0. Now, as I said, for any variational circuit, second thing you need is an observable. Over that observable, you find out a expectation. So we define these Pauli observables such that Z on the first qubit and I on rest other qubits. It mean that I want to find out the Z value corresponding to the qubit 1. Now Z value can be 0 and 1. So what do I want to find out? I want to find out how much my Z value or the first qubit value is closer to 0 or 1. Similarly, a Z in the second part represents Z value on the second qubit. So how much the second qubit behaves towards K0 or K1. Similarly for the third, for the fourth, for the fifth, and for the ninth. Now, we defined the observable. So we had the encoding, we had the trainable circuit, we defined the observable. So 3 main parts of a QVC algorithm is done here, right? Okay. Now we create an estimator. So here we use air simulator on 10,000 shots. So we use this estimator where we used air simulator to do the estimation of it running in its backend. Then we calculate the L1 loss. L1 loss is just some subtraction of the true value from the predicted value. So we put a L1 loss, and L1 loss is a classical loss. So it's not a quantum loss. So we measure the outputs, we get some values, we compare it with the target image. Again, we put that into the trainable circuit, and the trainable circuit modifies itself similar to a neural network. So what it does is it trains itself and updates its parameters automatically. So this is our training loss, and this is the final reconstruction image, and this is how the image would finally look and how the image was shown when it just started. Okay, so this was one part of it. I'll go to the code demonstration of it very fast. So this is the code demonstration of it. Can you see the code? Is it visible? Is the code visible? Can anyone please confirm? Is the code visible? Hello, is the code
Yes,
visible?
yes.
Yes,
Ji.
visible.
Okay.
Continue.
Thanks. Okay, so what we are doing is we are doing this, the thing that I showed you just now in the PPT, we are just doing it on the code. So first we are loading the Qiskit libraries and we are creating an image of our own. So we created this image. Now to put it into the circuit, first we need to have the linear value. So we flatten the image. After flattening the image, so see, we have the values 0, 1, 0, 1, 0, 1, 0, 0.75, 0. So see, 0, 1, 0, 1, 0, 1, 0, 0.75, 0. Now, we normalize the flattened image. So we see that as the minimum and maximum value was 0 and 1, so it retains the original value only. We created an encoding circuit and a parameterized quantum circuit. So see, ROI, this portion creates the encoding part. It's an angle encoding. And this portion creates the variational circuit part. So this portion will be trained. This portion will be used for the hyperparameter, that is for the non-training part. Now, after that, we visualize our circuit. You just saw this circuit I showed you in the slide a little bit ago. Okay, and we will be creating the Pauli observables over which we want to view the our final outcome. So see, these are the Pauli observables. I also showed this to you. Now, so this is the reconstructed image state vector. So we are declaring the state vector, getting the state vectors from its instruction set. Then we are putting the expected values here and we are reconstructing the image. So from the estimator, we are running through the circuit and see estimator.run times length of observables, comma observables. So we are getting the observables, storing the value of the observables inside the from the state vector inside the result, and we are reconstructing with the expected values. Okay, now see, we defined here the air simulator, use the air simulator in the backend, and number of shots we defined as something 10,000, and then with 10,000 shot 1 lakh shots, sorry, and then we declare a L1 loss. L1 loss, I said that is just the value minus the target. So what expected value we got minus what was the original value of the target, we calculated the L1 loss. And now so this was all defined, so we will put this into the actual working of the circuit. So we define the initialization of our parameters, that is which we will try to train. Then we will find, and this is the target image values, and then we'll just put it in the circuit, use Covila, and then we'll train it. So on training with L1 loss, we find out that its loss gradually decreases, and finally we will be getting this reconstructed image as the final result. So this was the code implementation of the slide that I just showed it to you. Okay, so this was on the simple implementation of an image reconstruction using a QVC algorithm. Okay, now I will also take you through the QNN part of it, and I will show the beauty of QNN and why it is so important to use some kinds of entanglements so that you could find the relationship between the data. So I'll take you fast forward through it. So we created some data. So what was that data? These are some images. Now, if you look carefully, there are some horizontal yellow lines and there are some vertical yellow lines and some horizontal yellow. There are many other images also. I'm just showing here 8 images. So we give them some labels, we create a VQC circuit. So first part of the VQC circuit will be for the embedding. So we create a Z feature map embedding here. This is the answers. What will the answers do? So we told that we need a parameterized circuit. That parameterized circuit will have its value updated as per the loss, right? So this is that parameterized circuit, and generally we call the parameterized circuit as ansage. So this is the ansage, and we will create a C0 list. So this C0 list is nothing but the entanglement pairs that we want to take custom. So what pairs are we taking? Between 0 and 1, 1 and 2, and 2 and 3. So if we see the circuit, so this is our entire circuit, but we have taken entanglement only between first two 0, 1, 2, and 3. So what is 0, 1, 2, 3? Let me tell it to you again. So if you look at this image, that is 0, 1, 2, 3, 4, 5, 6, 7. So if I am creating a link between 0 and 2, 3, that means I am only linking 0, 1, 2, 3. That is only the top row. Anyways, so then we try to run this circuit, and this is our final circuit that has been done by decomposition into the quantum hardware that we want to use. So we decompose that, we put a measurement, and then we run it, use the loss function here. So here we also use the mean square error loss. We train the circuit and use the optimizer. We ran it on IBM Torino, and after passing through the pass manager, we executed it using Qiskit primitives, and we find out that at the end of it, the loss that we will get has reduced, but the training accuracy is only 60%. Now, why 60%? So is 60% bad? Maybe 60% is a good accuracy for this thing, but we will observe a special kind of thing. If we improve that, we will see how this accuracy could be improved. Let us look into it. So we get accuracy around 60%, and we check our loss. We see that, okay, our loss is decreasing, but it has not decreased much. It has decreased up to 0.9 from 1. So that's not a big decrease in loss. Now, let us see how many images were not identified correctly. We found out 24 images were not identified correctly. If we look at the 24 images, can you observe a pattern here? The pattern is, see, this is in the second row, vertical, second row, vertical, second row, vertical, vertical, second row, vertical, vertical, second row, vertical. So whatever I'm saying, all of my words are going into two terms. One is vertical, one is second row. Now, if we observe carefully, we see that the vertical images are not identified. The second row is not identified. And if we look back into what we had done before, we can see that previously in our circuit, we have only entangled the first row and not the second row. So this is a very important thing. If we would have entangled the all rows, then the 24 misclassified images could be something different, but we find a pattern in the misclassified images where we see that specifically all errors are present based on the last 4 qubits. That is the second row. And if you see about vertical, it comprises of both the first and second row. So anywhere there is second row, there is an error prevalent. So what we did then, we created another entanglement set where we took all the possible rows one after the other. So see, we entangled all the possible rows. So from first, second, third qubit, that is for the first row, and fourth, fifth, sixth qubit, that is the second row. And we see that after doing that and continuing all the processes, we see that the loss has decreased from 1 to 0.8. So previously it was from 1 to 0.9. Now it is from 1 to 0.8. So we see that the loss has decreased further only because we put more entanglement into the second level also, that is second row also. And after all the training, we find out that the accuracy has increased to 80%. So I would conclude there is more work into it that is not required, but in this part, I will conclude this thing that why I showed this code work is because if you design a QNN circuit, it's not about getting just a result, it's identifying the relationship in your input data which you have to identify properly so that you could actually use this circuit to find out something important. So what would you have done if this was a classical program? So if it would have been a classical program, it would have been dependent on data. So more number of data you have, the better outcome you will get. But in quantum, it's not about data, it's about how you design your circuit based on your input data. So if your input data is such that it has relationships between first and the last qubit, you should design your circuit in a way so that you could create a relationship between your first and the last qubit so that that relationship could be identified properly. So the main point from today's class is that we should create our circuit intelligently so that it is able to identify the patterns in our data, and the type of data that we use will have that relationships inherent in between them. So yeah, that's all for today. Thanks to all of you, and the QML class closes here. Thank you.
Please, a round of applause for Sudikin. I have learned so much in this journey with you, Sudikin. Things I thought I understood that I understood completely different. And I think that everyone is always looking for more time with you, giving your depth of knowledge in physics and quantum machine learning, geospatial, everything. We are so lucky to have you presenting. So thank you so much for culminating this quantum machine learning course. We heard from our speaker Gian on some financials. You heard from Daniel Ruiz today on the critical algorithms that you can also use, like BQE. You saw real world applications, products, people making money on this. It's incredible. There is so much you could do. Material science, Danielle, actually, I think this also concludes the VQE portion, right, for quantum chemistry? Yeah. So
I
let's
think
give
so.
also Danielle Ruiz from QNow a round of applause for all of the expertise and time and dedication. This is a labor of love, I tell you all. We are volunteers. We have lives and children's and families, and it is out of passion for science and all of this that we bring these programs to you. So please make good use of the Discord, ask questions. It dawns on me that until you take the test, you may not realize the questions you have. So hopefully by this weekend, when you take the fundamentals quiz and then you attempt to go for the badges, that you take advantage while we have support in our Discord channel to ask the questions that you can. We are going to dive deeply into cryptography for next week and some of KQD and PQC, kind of showing you some roadmaps. We're going to launch the rest of the hackathons. Today, we'll put one out there so you can get started, have time to, let it kind of sink in. And for those of you who had previously participated in this humanitarian challenge, I really invite you to take some time to take a walk, put your feet on the ground, think about the things that you really would like to make better in the world that we live in, and know that we have some amazing prizes for you. So more to come on that, and stay tuned for the recordings. I'm putting the interim recordings with Zoom over there. Just select your language, and we were having some issues with the compilation of some of the language files, so spare with me for the YouTube, but further than that, you'll get it real time. As soon as this comes up, I will put it there so you can watch it. Wonderful.
Ma'am,
Yep. Go ahead.
I have something to show.
Oh boy.
Sorry, where is that?
Oh, yay!
And the hooks.
Can you okay? I don't know whether it can be seen or not. It is not taking properly. Okay, anyways.
Oh, wonderful. You have to
Okay.
open it. You have to open it. The grand reveal.
Yes, yes, please.
Okay, let me can I, my background is not that good, so let me remove it. Just 1 second.
Oh, don't worry. You don't have to. Yeah, you can. You don't
Yeah.
have to. Here, let me pause the recording.